Here are two circuit problems to solve. Circuit 1 and Circuit 2, and I want you to do these two steps. Explain how you can solve each problem. So in a written or verbal statement, explain in words how you're going to solve Circuit 1 and Circuit 2. And then outline a procedure you will follow. List the steps that you're going to follow in solving each of these circuits. Once you've done that, you can come back and go to page 2. Okay, here's the two circuits, and let's make some statements about each one of them. This circuit here, circuit on the left, is as simple as we can get it without using Kirchhoff's laws. We can't use Ohm's law to simplify this circuit anymore. It has two power supplies and three resistors, none of which are in simple series or parallel arrangement. So the method for solving this circuit is outlined down here. One, we're going to solve it by means of Kirchhoff's laws. So the first step is to label the currents in the circuit. So that's what I'll do. And there are three currents, one here, and one here. Two junctions, three currents. And the second step will be to write, since there are three currents and three unknowns, we're going to write three Kirchhoff laws equations. And when we do that, we'll see that there's going to be one junction equation, Kirchhoff's current law, which states that the sum of the currents into a junction is 0. Currents in are positive, currents out are negative. Or an alternative way of stating Kirchhoff's current law is the currents into a junction must equal the currents out of a junction. This, of course, is based on, I didn't write it, but I'll add it now. This is based on conservation of charge. Any charge that goes into a junction has to come out of the junction. That will give us one equation, and we'll get the two others using Kirchhoff's voltage law or the loop rule, which says that the sum of the voltages around a closed loop will be equal to 0. And so we'll get two more equations when I do this problem by taking the currents around the left-hand loop and the currents and the voltages, the voltages around the right-hand loop. Notice there is also a loop here, but all we need is two loops, so we'll take the left-hand loop and the right-hand loop. And that will give us our three equations. And then the last step will be to solve three simultaneous equations by whatever methods you choose. Circuit 2 on the right should be simplified first, so I didn't put that down. Let me write that down. So in this case, the first step, since I have steps 1, 2, and 3 there, I'll call it step 0. And that would be to simplify the circuit. And we do that, we can see that this branch of the circuit has two resistors that are in simple series, so they combine to a single resistor. This branch of the circuit has only one resistor, so that stays the way it is. And this branch, which has the same current all the way from here to there, these three resistors are all in series in this part of the circuit. Even though this one is on a different side of the battery, the same current goes through all three resistors, and we can add those together to get this. And once we've simplified this circuit to this circuit, then it has the same form as this one, and the same methods would be used to solve it. So let's go to the next page. And on this page, I'm giving you a circuit similar to either of those on the previous page, but I've put numbers in. So what I want you to do now is to pause the video and go through the steps, the 3 steps outlined on the previous page, and try to solve this circuit. Pause the video and do as much as you can before you come back to look at my solution. Okay, here's the solution. 3 steps. Label the currents. Write the 3 equations. There are 3 currents. And then use some method to find the solution of those simultaneous equations. So we have 2 junctions and 3 currents. Starting at this junction, going through the battery and through R1 is a single current I called I1. There's another current starting at this junction, going through the battery, through resistor R3, and into this junction that we called I3. And since both of those are going in, I2 must come out of the junction and go down. So you can see current is circulating this way and current is circulating that way. And so by the junction rule, I1 plus I3 should equal I2. I1 and I3 go in, I2 comes out. Then we do the left-hand loop rule starting here. We go through the battery, that's 4 volts. We go through this resistor in the direction of the current. I forget to mention that in the direction of the current is positive and opposite the current is negative. So we have the voltage drop across here is going to be the current times the resistance. And it's a drop, so negative 2 ohms I1. And then we have negative 4 ohms I2. That all has to equal 0 by the loop rule. And if we go through this loop starting here, going through the battery, going through R3, going through R2, and back, closing the loop, we have 6 volts here, 6 ohms times I3 would be the voltage drop across that resistor, and 4 ohms times I2 will be the voltage drop across that resistor, and all those voltages have to equal 0. Okay, now where I see I2, I'm going to substitute in, now we're at the solution part, right? We have the 3 equations, 1, 2, 3, and the rest is linear algebra. So here's I2. I substitute in for I2, I1, and I3. And so the negative 4 ohms times I1, negative 4 ohms times I3 eliminates I2. And I do the same thing over here. I2 goes to I3 plus I1. Then in this equation I have 2 terms in I1, so I combine them, 2 ohms and 4 ohms, 6 ohms I1, 4 ohms I3, and the 4 volts. So this is my new equation where I've eliminated I2, and I do the same thing over here, combining these 2 similar terms for I3, and I get 6 volts, bringing this over here to put it in the right numerical order. 4 ohms I1 and negative 10 ohms I3 equals 0. Then I use this method to solve the equations. I want one of the terms to cancel, so I look at this as 6I1 and this is 4I1. So if I multiply this equation through by a negative 1.5, the 6 becomes a negative 9, the negative 4 times negative 1.5 becomes a 6, and the 10 times 1.5 becomes a positive 15. I bring that equation over here, and I subtract the bottom equation from the top equation. I subtract the equation for the right loop from the equation for the left loop, and I've set it up so these two terms will go to 0. So negative 9 plus 4 gives a negative 5. These two terms add to 0. This is negative and positive. These add to 11 ohms I3. And now I just solve for I3, and I get that I3 is 5 volts over 11 ohms, or 5/11 amps, or 0.45 repeating. I take this number for I3, and what I did was I went up here and I substituted this number in here. So now this is a number. It's going to be 4 times this number. So 4 times this number will give me 20/11 here, and 4 volts there, and 6 ohms I1 there. And when I do that out, I end up that I1 is equal to 4/11, 4 volts over 11 ohms, or 0.36 repeating amps. And I2 has to be the sum of those two, so when I add the 5/11 and the 4/11, I get 9/11 amps, or 0.81 repeating amps. So that's the solution to that problem.